In this video, we're going to explore the mechanism of a molecule that comes back a lot in organic chemistry too, and that is NBS. Now, to understand why we even need to talk about this molecule, we have to go back a little bit and talk about the stability of different radicals. Remember that the more substituted a carbon is, the more stable the radical will be that forms on it. So for example, this radical here, that is only bonded to one carbon, so it's primary, and it's not very stable. The next one is bonded to two carbons, so it's secondary. That radical is a little bit more stable. The next one, you have three carbons there, so that's tertiary. That is even more stable because the radical is able to spread out through hyperconjugation. And finally, at the end, if you have a radical on an allylic position, it is the most stable radical of all, because the radical exists in a p orbital that is parallel with the p orbitals in the pi bond that it's allylic to. And so it's able to spread out over all three of those atoms through resonance. So an allylic radical is the most stable radical of all. An allylic radical is one that is one atom away from an atom in a pi bond. Okay, and so what that means is, if you remember when we do radical reactions, you form the radical and you add the halogen where the most stable radical forms. And so if you ever have a pi bond in a molecule, you will form the radical and add the halogen at the allylic position, because that's the most stable radical that could form. So let's say you have an alkene rather than an alkane, and you treat it with Br2. This is a reaction that we know from the alkene addition chapter. This is bromination. You can take your original molecule, erase the pi bond, and add the two bromines anti to each other. So if you add Br2, you would get the two bromines anti to each other. And in this case, you would also get the enantiomer. Okay, what if you take that same reaction, so you still have the Br2, and as the Br2 knocks into the alkene, you still get this dibromo product. But in addition to the bromine, you add the light, H nu, Planck's constant times the frequency of the light. You add light in order to create radicals. Well, in that case, you would add a bromine where the most stable radical would form. That's on the allylic position, right? That allylic position is where the most stable radical could form, and so that's where the radical will form, and that's where the bromine will attach. So you have these two reactions that give you very different products. You have the addition reaction that gives you a dihaloalkane, and you have the radical reaction that gives you a haloalkene. Now, if you just mix these reagents together, an alkene with bromine and light in a container, sometimes the alkene will react with the regular bromine and do the addition, and sometimes it will react with the bromine radicals and do the radical addition. And so if you use just molecular bromine, Br2, as your source of bromine radicals, then you end up getting a messy mixture of products. And the more messy your products are, first of all, the more time-consuming the reaction is, and second, the more expensive it is, because it's more time-consuming. And so the less useful your synthesis is. So to overcome this mess, chemists have found a different source of bromine radicals. Instead of just bromine molecules, they use another molecule called NBS. And NBS stands for N-bromosuccinimide. The N and the B tell you about a crucial feature of the molecule. In the molecule, you will have nitrogen bonded to bromine. N-bromo, bromine on a nitrogen. Succinimide that's referring to a 5-membered ring, with the nitrogen being one of the atoms in the ring. And on either side of the nitrogen, on each of the carbons next to it, you will have a double bond to an oxygen, and that's the succinimide part. So, that molecule is N-bromosuccinimide. You'll definitely want to be able to draw N-bromosuccinimide. What you'll notice is that this nitrogen is allylic to both of the carbonyls. The nitrogen is one atom away from this carbonyl and one atom away from the other carbonyl. And so if you have a lone pair or a radical that forms on that nitrogen, then it can be stabilized over all 5 of these atoms through resonance. And so it only takes a little bit of light, H nu, to vibrate this bond. Those bonds are like springs. As you vibrate them, the string goes back and forth, back and forth, back and forth until it pops, until it's homolytically cleaved. So if you add a little bit of light, N-bromosuccinimide, NBS, will cleave into 2 radicals. You'll have the succinimide radical, and you'll have the bromine radical. Now this already had 3 lone pairs on it, so I'll have those 3 lone pairs here, but now in addition to those, you'll have the unpaired electron on the bromine. So you have formed 2 radicals. Now, whenever we use NBS, N-bromosuccinimide, this is going to be our initiation step. Our initiation step will always look like this. This is always the first step of any mechanism that uses N-bromosuccinimide. And so you can see that N-bromosuccinimide, because it has these carbonyls here, the radical that you form is stabilized through resonance, is allylic to both of these pi bonds. It's one atom away from both pi bonds. And so it spreads out over all 5 of those atoms. That stabilizes this radical and makes it easier for these to form. Because if this is stabilized, then it won't immediately stick back to the bromine. It'll let the bromine escape. And so you can form bromine radicals this way. And the nice part about this is that in this reaction, that limits the amount of bromine that can undergo this addition reaction. And it prefers the radical reaction. So the magic of using N-bromosuccinimide is that you end up getting the radical products more efficiently. You don't get the addition products so much anymore. So that's what NBS is, N-bromosuccinimide. It's a source of bromine radicals, and it's really useful because it allows you to form allylic radicals without competing addition reactions. So allylic radicals rather than the addition products. Okay, so given those things, here we're going to have some alkenes, and we're going to use NBS and light that says draw the mechanism and predict a product for the reaction when each of the following molecules is treated with N-bromosuccinimide and irradiated with ultraviolet light. So we're going to treat each of these with NBS and light, H nu, Planck's constant times the frequency of the light. All right, well, first, we know that these radical reactions always involve 3 steps. They have a beginning, a middle, and an end. The beginning, the first step, is called the initiation step. So I'm going to draw initiation. That's the beginning. After that, we're going to have the middle, which is the propagation step. And then at the end, we will have the termination step. The initiation step is the step in which you create radicals, and so the step is really going to be the same as what we drew above. That will always be our initiation step when we use N-bromosuccinimide, or NBS. So you'll want to be able to draw N-bromosuccinimide. NBS tells you where to start in your drawing. You have a nitrogen bonded to a bromine. The nitrogen is part of a 5-membered ring, and on the carbons next to the nitrogen, you have double bonds to oxygen. A carbon double bond to an oxygen is called a carbonyl. Carbonyl. It's a useful feature that appears in a lot of different functional groups. It's not a functional group itself, but it appears in a lot of them. So it's useful to know that carbon double bonded to oxygen is a carbonyl. So you'll shine light on this and you will get homolytic cleavage. One of the electrons in this bond between the nitrogen and the bromine, one of those electrons will go on the bromine, the other electron will go on the nitrogen. And you end up forming 2 radicals. You form, and this bromine had 3 lone pairs to begin with, so you form a bromine radical, and you form the succinimide radical. So that's the initiation step. Homolytic cleavage to give you 2 radicals. You're starting the story of this radical reaction, initiating it. Once you have your 2 radicals, you can use those to create the reaction with whatever carbon molecule they give you. So let's copy this carbon molecule down. We have this sort of 5-membered ring, the 2 methyl groups, the pi bond, and we know this is going to react with the least stable radical. That's going to be the bromine. The succinimide is able to stabilize that radical through resonance over those 5 atoms. The bromine is only able to stabilize the radical by spreading it out over its enormous volume, space that it takes up. So the bromine is a little bit more reactive, and this bromine is going to be bouncing around. This other molecule bounces around. Eventually, they slap into each other, they knock into each other, and they do this over and over and over again in different places. And statistically, the reaction that happens most often is the one where this rips a hydrogen off and you get the most stable radical left. Now, because we have a pi bond, the most stable radical will form on the allylic position. The allylic position is an atom that is 1 atom away from an atom in the double bond. So here I've highlighted the 4 allylic positions on this molecule. You'll remember that these radicals react with the first thing they run into, and that's usually a hydrogen. Because hydrogens are on the outside of a molecule, and this will bump into the outside of a molecule first. Now, you don't see a hydrogen in either of these allylic carbons at the top, so it won't be able to steal a hydrogen from those. You'll notice that these on the bottom do have hydrogens, and it doesn't really matter which one it steals from because the molecule is symmetrical. The left and right sides are the same. So even if we just show, for example, it's stealing a hydrogen from this molecule on the right, this hydrogen on the right, if we take this and, like with a spatula, flip it like a pancake, it will be as if it were on the left. So I'm going to draw one of those hydrogens there. That's going to be the hydrogen that this radical rips off of the molecule to stabilize itself. So you're going to form a new bond. Anytime you form a new bond in a radical reaction, one radical donates 1 electron. The other atom donates 1 electron. Notice I'm using fishhook arrows, and they're pointing to the space where the new bond would form. This bond that has the hydrogen in it, we're removing 1 electron from it. The other electron snaps back onto the carbon. And so this is a hydrogen abstraction. What you get after that is, first, this bond breaks. One of the electrons goes onto the allylic position, so that's a radical that's stabilized. The other electron joins with the other radical to form a new bond between the hydrogen and the bromine. So now we have this hydrogen bromide and a carbon radical. So that's a first propagation step. Remember that in the propagation steps, you start with one radical and you end up stabilizing that and creating another one, a different one. Okay. Now, for the rest of this, I'm going to simplify it ever so slightly. It will still represent the essence of this reaction. We're going to take the succinimide radical and we're going to react it with the hydrogen bromide. So this is going to be a second propagation step. So in these reactions with NBS, you'll not just have one, but you'll have two, and you'll have two propagation steps. So in this step, the succinimide radical is going to rip a hydrogen off of the bromine. So it uses its one electron to form a bond to the hydrogen. It steals one electron from the hydrogen, and the other electron in that bond snaps back onto the bromine. So this is just a very similar. Compare these arrows to these arrows up here. They're very similar. You might pause the video and compare those. So you'll see that they both form a new bond with fishhook arrows pointing to the space where the bond is forming, and the bond that they're breaking has a radical snapping back onto an atom. So here, you end up breaking this bond. The radical forms a new bond to the hydrogen, and the other electron in the bond forms a bromine radical again. So that's the second propagation step that you would want to be able to draw in this mechanism. Okay. So now we create this, what's just regular old succinimide. Notice it's different from N-bromosuccinimide because it doesn't have the bromine attached to the N, the nitrogen. So now that we have these, we've created two radicals, this carbon radical and this bromine radical. We're ready to put them together and end this radical reaction. We're ready for the termination step. So in the termination step, two radicals combine. And by combining, you destroy the radicals. Everyone's electrons are going to be paired. So we take the carbon radical that we formed in the first propagation step, we take the bromine radical that we formed in the second propagation step, and those two radicals are going to pair up. The one electron from the radical on the left will donate one electron, the radical of the bromine will donate a second electron, and those two molecules will form a new bond to each other. So you end up with a bromine attaching to the allylic position. Now we just drew this mechanism, and let's quickly review what we did. We had an initiation step where light homolytically cleaved the bond between the nitrogen and the bromine on N-bromosuccinimide, created two radicals. The bromine radical ripped a hydrogen off of the allylic carbon of the carbon chain and created an allylic radical in HBr. The succinimide radical steals the hydrogen from HBr and recreates the bromine radical. Then the carbon radical and the bromine radical that you formed in the two propagation steps pair up in the termination step to add the bromine onto the allylic position. Now, if you're just thinking of this in terms of synthesis, what you accomplish as you go from the very beginning to the very end, what we did was we took this carbon chain we treated it with NBS and light, H nu, and what we got was a bromine on the allylic position, the position where the most stable radical would form. And so this is another way to think of this reaction from the perspective of synthesis. In this particular exercise, we looked at the mechanism, because they're asking us to draw the mechanism, but we can also predict the product. That's a separate thing, just by looking at this overall synthesis transformation. Okay, so let's draw that mechanism two more times. As we apply it to two different molecules, you'll see the similarities. Now the first similarity is, so we're going to treat this molecule with NBS and light, H nu, Planck's constant and the frequency of the light. And what's going to happen? Well, yet again, we're going to have these three steps: initiation, propagation, and termination, the beginning, middle, and end of our radical reactions. When you use N-bromosuccinimide, NBS, the beginning, the initiation step, is always homolytic cleavage of the bond between the nitrogen and the bromine to form these two radicals. So you'll redraw N-bromosuccinimide. You'll show one electron in the bond going onto the bromine, the other going onto the nitrogen. And the reason why that's happening is because light is shining on that, making this bond vibrate faster, faster, faster until it snaps. Okay, so that's the initiation step. Now, let's think about the propagation step. We're going to have two propagation steps. In the first propagation step, we're going to take our molecule. I'm going to copy that down. So let's actually do this from scratch. So I'll redraw that molecule. Redraw that molecule, just a second. All right, cool. So that's our molecule. And the bromine radical is going to rip off a hydrogen from this molecule. It's going to rip off a hydrogen that will give you the most stable radical. Oops. So this molecule, the bromine's knocking around in a gigantic galaxy-sized mosh pit, this other molecule knocking around. As they knock into each other, the bromine tries to snatch hydrogens off of the molecule, and it does that most often for the hydrogen that is most vulnerable. The most vulnerable hydrogen is the one that leaves behind the most stable radical. And we saw that the most stable radical is an allylic radical. The radicals become more stable as the carbon becomes more substituted. The allylic radical is the most stable of all of them. So, in this propagation step, we're looking at this. We have a pi bond, so we know we have an allylic position. We actually have two of them. Both of those carbons are allylic. They're one atom away from this atom in the double bond. So, which one will the bromine steal a hydrogen from? Well, the one on top does not have a hydrogen. It's buried. It's very crowded. It has a carbon on four sides. Notice, It's bonded to 1, 2, 3, 4 carbons. It's quaternary. And so it's buried in the inside of the molecule. As this bounces around, it can't reach it. It would knock into one of these other carbons first. So there's no hydrogen there for this bromine to steal or abstract. The other allylic position, though, does have hydrogens, and so that's where the bromine is going to rip a hydrogen off. So the bromine is going to form a new bond to that hydrogen, and at the same time, the bond that the hydrogen is in will break through a radical mechanism. So the bromine donates 1 electron to the bond, the hydrogen donates another electron to the bond. Notice I use fish hook arrows for that. And the second electron in this purple bond, going to the hydrogen, that breaks that last second electron, snaps back onto the carbon there. And so we form a new bond between the hydrogen and the bromine. And the bond that was in the hydrogen breaks, and we have a radical left on that allylic position. Notice how this is 1 atom away from an atom in a double bond. So that's an allylic radical, and it's spread out through resonance over all 3 of those atoms. Oops. Okay, so we form our carbon radical in that first step. Now in the second step, we take the succinimide radical, and we're going to react it with this hydrogen bromide that we formed before. So we have 2 propagation steps in this mechanism. The succinimide is going to steal the hydrogen, so it'll contribute 1 electron to a new bond. The hydrogen will contribute a second electron to a new bond, and the second electron in the bond that the hydrogen already has snaps back onto the bromine to create a new bromine radical. So this bond breaks, hydrogen contributes 1 electron, nitrogen contributes 1 electron to form a new bond between the nitrogen and the hydrogen. So now we just have succinimide, regular old succinimide, no bromine on the end, or nitrogen, and bromine turns into a radical. Okay, so that's the middle of our story, the 2 steps in the middle, the propagation steps. At the end of our story, we're going to have a termination. It's always the last step in any radical mechanism. And in the termination step, the 2 radicals that we form in the propagation step couple. They come together. So this carbon radical will come together with this bromine radical to form a new bond to each other. That will destroy the radicals, so that they'll pair up and you won't have the radicals anymore. And so that ends or terminates this reaction. The carbon donates 1 electron, the bromine donates the other, so you create a bond between those 2 atoms. And that's your product. So we had our 3 steps. The initiation step, where we created radicals from N-bromosuccinimide, homolytic cleavage of the nitrogen to bromine bond, represented in the name. The propagation step, where the bromine radical rips a hydrogen off of the carbon chain, the allylic carbon, and that becomes a radical. Succinimide steals the hydrogen from HBr and reforms the bromine radical. And then the carbon radical and the bromine radical that we've formed in the propagation steps, those pair up in the termination step to give us the alkyl bromide. Notice that when you think about this reaction overall, what did you accomplish? What did you start with? What did you end with? we started with this alkene. We treated it with N-bromosuccinimide and light, H nu, and we ended up with, and what the product was we added bromine onto the allylic carbon. The allylic carbon that had a hydrogen on it. All right, one more. Let's repeat that just to build confidence, build muscle memory. Let's repeat that process with this last alkene. So what would happen if you took this alkene, you treated it with N-bromosuccinimide in the presence of light, H nu. H is Planck's constant, and nu is the frequency of the light waves, how frequently they hit you. Well, anytime you have a radical reaction, and when you see NBS, you want to think, okay, that's going to be a source of bromine radicals. Anytime you have a radical reaction, you have 3 steps: the beginning, the middle, and the end. The initiation step, the propagation step, and the termination step. In the initiation step, if you have N-bromosuccinimide, the initiation step is always the breaking of the bond between the nitrogen and the bromine on N-bromosuccinimide. You shine light on that, that vibrates this bond faster and faster and faster until it bursts open. One electron goes on the bromine, the other goes on the nitrogen. You create 2 radicals. The bromine is able to stabilize the radical by spreading it out through its enormous volume. The nitrogen is able to stabilize the radical because it is allylic to 2 pi bonds, and so it spreads out through resonance. That's always the initiation step whenever you use NBS, N-bromosuccinimide, in a radical mechanism. Okay, now that we have our radicals that we formed in that homolytic cleavage of the initiation step, we can think about the middle of the story, the propagation step. And when you use N-bromosuccinimide, this has 2 separate steps that you want to draw in. So let's draw these from scratch. So here we take, now that we have our radicals, they're going to react with the carbon chain that they gave us. So I'm going to copy that carbon chain down in this propagation step. And the bromine radical is going to rip off the most a hydrogen from this molecule. Bromine radical is bouncing around, the alkene is bouncing around, they smack into each other over and over and over again. Statistically, the bromine radical rips off a hydrogen, the hydrogen on this carbon chain, that leaves behind the most stable radical. Well, we know that the most stable radical is the allylic radical. We see a pi bond, and we notice that the carbon 1 atom away from it is the allylic position. Now notice that this molecule is symmetrical. There's a symmetry here. And so both of these 2 positions are really the same. If we think about this position, and you sort of take a spatula and flip this molecule over like a pancake, well, then it becomes this other position. So it doesn't matter which allylic position we choose in this example, both of them will give us the same product. So we draw the hydrogen in, and the bromine is going to rip that hydrogen off. The bromine is going to bond to the hydrogen. It contributes 1 electron, the unpaired electron of the radical. The hydrogen contributes 1 electron, and the second electron in the hydrogen's bond snaps back onto the carbon. So, propagation step. What we end up with is this bond breaks. One of the electrons goes onto the tertiary and allylic carbon, and the hydrogen donates 1 electron, the bromine donates 1 electron. You create a bond between the bromine and the hydrogen. So that's our first propagation step. There is a second propagation step where we take succinimide. So we used our bromine radical. We take the succinimide radical that we formed, and we're going to react that with HBr. And this is going to be another propagation step, so this nitrogen is going to rip off that hydrogen. And so it's going to bond to it. The nitrogen will contribute 1 electron, the hydrogen will contribute 1 electron, the other electron in this bond will go onto the bromine. So we have two things here. This bond breaks. One of the electrons goes onto the bromine to form a bromine radical, and the electron from the hydrogen, the electron from the nitrogen pair up to form a new bond between the nitrogen and the hydrogen. So we get succinimide here. Not N-bromosuccinimide, just regular succinimide. You'd have to attach a bromine to the nitrogen to get N-bromosuccinimide. So overall, in the propagation step, we formed 2 radicals, a carbon radical and a bromine radical. Those 2 radicals pair up in the end of this, in the end of this story of this reaction, the termination step. So we get the carbon radical and the bromine radical. And those are going to pair up or bond to each other. That will destroy the radicals because all the electrons are paired, there's no radicals anymore, and terminate or stop the reaction, end the reaction. So the carbon donates 1 electron, the bromine donates another electron. Notice they both point to the space where the bond is forming. And what you end up with in that termination step is a bond between the carbon and the bromine. Okay, so we had 3 steps. We had an initiation, propagation, and termination step. In the initiation step, N-bromosuccinimide homolytically cleaved the bond between the nitrogen and the bromine to give us 2 radicals. In the propagation step, each of those radicals underwent a reaction. The bromine reaction rips a hydrogen off of the position of the carbon that will leave behind the most stable radical, the allylic position, and we form a carbon radical. We also form HBr. In the second step, the succinimide radical rips the hydrogen off of the HBr and gives us our bromine radical back. And finally, in the termination step, the carbon radical and the bromine radical pair up and leave us with an alkyl bromide. So if we think about what we achieved overall in this reaction, we can take that hydrocarbon that we started with in the very beginning, we treated it with N-bromosuccinimide in the presence of light, H nu, and we ended up with the same molecule, but with a bromine on the allylic position. So N-bromosuccinimide is a way to efficiently add bromines onto the allylic position without having to worry about competing addition reactions. These competing addition reactions that we would get if we just used molecular bromine. So NBS with light will give us the radical product. And hopefully these exercises in this video clarified how and walked you through how to draw the mechanism for these N-bromosuccinimide radical halogenation reactions.